In this video, I'm going to talk about brake design starting from scratch. So I'm going to get into it with Excel. So we have some parameters for the car. Rotor center line diameter, not the overall diameter, but from the pad contact area, the center line of the rotor diameter. And wheelbase, CG, weight distribution, front and rear weights, which are calculated off of the vehicle mass. And then we have tire diameter. You can use whatever units you want to use. It doesn't have to be metric. It can be inches or a mixture, but just be careful that you keep track of it for calculations to come. So here we have the pedal force and a pedal ratio. For pedal force, I said 310 max because I don't want the driver's leg to get tired. Think about doing a one-legged squat, or if you go to the gym and use the leg press machine, put some weight on there, push it with one leg and see how hard it is, and if you'll be able to continuously and consistently apply that force without getting tired. Especially if you're doing some kind of endurance driving, you don't want 150 pounds or whatever, some high amount of force that you gotta consistently put on the pedal, because you're gonna either get tired or you're not gonna be able to put that force on evenly lap after lap, turn after turn. So you can find the pedal ratio mathematically doing geometry for your setup. So we can do it in CAD as well. So in this sketch, what we have is the brake pedal with the mount for the master cylinder, and this line's the master cylinder itself with the pivots here and here. So it's just a rough drawing of a setup for the master cylinder and brake pedal. So let's say the pedal moves 10 millimeters. We'll take the starting master cylinder length, move 10 millimeters, take that number. So we get a pedal ratio here of 7.3 basically. And you can adjust your dimensions to get the pedal ratio that you're looking for. So that's like a graphical method to do in CAD if you don't feel like doing geometry, but either way works, and it's really for what's going to work best for you, what you need. So next we go into front and rear master cylinder diameters, which you're going to look at a manufacturer, who you want to buy your master cylinders from, and they have sizes already made, so you're kind of stuck with those sizes. So in this case, 5/8 for the front, 1 1/8 for the rear. So if we take the pedal force times the pedal ratio and divide by 2, because that force is getting split into the front and rear master cylinders, divided by pi r squared of the master cylinder diameter, which is area. So you have a force divided by area, you're getting PSI, so the line pressure for the front. Do the same thing and you get a line pressure for the rear. So next we have the front and rear caliper diameters. Same as the master cylinders, if you're buying from a manufacturer, there's set sizes that they sell. There's no in-betweens. So in this case, a 1 1/8 caliper piston diameter. We have the number of pistons per caliper. So if we take the line pressure, PSI, times pi r squared, r being the radius of the caliper, times the number of pistons per caliper, we're getting a force that the piston is pushing the brake pads against the rotor. And we'll do that front and rear again. And I've split it up here. Front left, front right, rear left, rear right. So moving on, if we take the pad force times the pad coefficient of friction, we're getting the force that's actually put on the rotor surface between the brake pad and the rotor surface. And then we are taking the rotor center line diameter divided by 2 to get the radius. And here I'm dividing by 1,000 just to make millimeters into meters. So it's a force times a distance. We're getting a torque. So this is the torque of the rotor. So again, front left, front right, rear left, rear right. So we take the rotor torque, divide by the tire radius. Again, I'm doing divided by 2, and also divided by 1,000 to make millimeters into meters. Then we'll get the tire force of the tire against the road surface. And we can find the percent front, just the front divided by the sum of all the force. We're getting 79.5% of the braking is being done by the front. If we take the tire force divided by the vehicle weight, so the mass times 9.81 for gravity, so you make that vehicle mass into a vehicle weight, then we're getting our G's. So 1.5 G's. So this number's saying you don't have tire data, but you know what kind of car you're making, and looking at similar cars in your class, you know they break around 1.5 G. You can use that number as a starting point. If you don't have tire data, the only thing you have to go off of is other cars racing in the same class as you. So next we can calculate weight transfer from that longitudinal G. So we're taking the CG height times the G's times 9.81 for gravity to make that G's into meters per second squared, times the vehicle mass, and you're dividing by the wheelbase, and that'll get you longitudinal weight transfer. So we'll take our front weight divided by 2 per corner, and same with weight transfer divided by 2 to make it per corner. And you add those, add the weight transfer to the front, because you're braking, weight transfer's going forward, and you'll get the front corner weights with weight transfer. Do the same for the rear, but you subtract the weight transfer. So now we have the normal load on the corners, and we can take the tire force divided by the normal load, and that'll be our coefficient of friction on the tires. So in this case, it's right under 1.5, and we know we're doing 1.5 G, so that's about where you want to be. Let's say you're in this case 1.52 G, and you look here, you see your coefficient of friction is 1.6. Your tires probably can't do that because you're expecting 1.5 G. So it's just saying actually the rear would be locked up because they're not able to provide that coefficient of friction. So you can adjust your rotor centerline diameter. You can change your front or rear mass cylinder, make them, so I'll move this back as an example. So we're saying 1.6 for the coefficient of friction, which we know is too high. The tires couldn't handle that. You can make the front mass cylinder bigger, because that's going to give you less line pressure. Remember, it's pounds coming from the pedal force and ratio divided by this area, gives you pounds per square inch, or whatever units you're using, PSI in this case. So we made this bigger, which reduces the line pressure, which then reduces the rear rotor torque, and we can check our coefficient of friction. It went down. And then we could adjust rotor center line to either get that back up to 1.5, or we can use the same mass cylinder diameter and just change the rotor size. And it could take some iterations till you find this. And here we see the front coefficient friction is a little higher than the rear. So this is going to meet the limit of the tire before the rear, which I would always have the front lock up before the rear. If the rear locks up, you don't lose friction, it reduces. So the rear friction reduces, which could cause the rear end to come around and you'll spin out. So I'd rather have the front lock up and the rear not locked, so you have a stable platform because you still have rear friction. So there's basics. You can use this and make a brake system for your car, and it'll work. It's not 100%, but it'll get you really close, and you'll have a usable brake system here. But we can also take it one step further. Let's say we have tire data, and we know how the coefficient of friction reduces when you add normal load, which most tires do. As you increase the normal load, the coefficient of friction actually decreases. So if you have tire data, then you can make a graph like this and use whatever. I have this formula. You can make whatever formula fits your tire data. So what we do here with the formula for the tire coefficient of friction, we do everything the same. Find the normal load from the weight transfer, plug it into our tire formula for the coefficient of friction, and we can see the max tire force for this given normal load, and we can compare it to what the brakes are providing. So we see the maximum is higher than what the brakes are performing, so they're not locked up yet. You can also do the coefficient of friction using that same formula that fits the tire coefficient of friction, and we could subtract what the tires can provide from what the brakes are doing. Just all of this here is what we calculated before. We're just adding in coefficient of friction using our tire model, what's fit to the curve for coefficient of friction and normal load. We could subtract those, and then we can see how close we are to getting them to lock up. Where you see the rear still has a little bit more to give than the front. So if we increase our brake force a bit, so we just increase it until we can see when you get a negative, that means that end of the car is locked up. So we have the front locked up before the rear. So this is if you have tire data, you can use this to help design your brakes. Where it's ended up being a little different than the one we did before, where we just assumed that the tires have 1.5 coefficient friction max of 1.5, where in this case, you see the rear has a little bit more, the front has a little bit less, and that's just from this tire model. And also if you have this, you can actually find your max braking. In this case, 1.49 is the max that these tires could give this particular car. So now we can take it one step further. If you have a lap time simulator, such as Optimum Lap, which is free, there's also other online calculators you could use, or if you have one that you made yourself, you can use that. So we're just going to export the results and save them, and then we're going to use those to further design our brake system. So from our lap time simulator, I'm going to take time, longitudinal acceleration, speed, and Optimum Lap gave me brake position, so if the brakes were on or off. So for all the corners, front left, rear left, rear right. So if we take the acceleration times it by our vehicle mass times percent front brake, and we're going to divide by 2 because we don't want total front, we want one corner of the front. We do that, and same for the rear, but you subtract 1 minus the 78% because you're taking the rear now. We'll get the tire force, so the force of the tire against the road surface. And then from here, we take the tire force and times it by the tire diameter, or the radius. Again, divide by 2 to get the radius, divide by 1,000 and make millimeters into meters. And I did negative on the tire force just because it is braking, so it would be a negative tire force depending on your coordinate system. So using that, we get rotor torque. So if we take our rotor torque, multiplied it by vehicle speed divided by the tire radius, again making it into the diameter in millimeters to the radius in meters. So you're doing a torque times a rotational speed, radians per second, and you multiply it by a change in time, we actually get energy. So we got all the energy for all the corners of the rotor. So that's the energy going into the rotors. All right, for the brake temperatures themselves, we have this formula, Q equals C times M times delta T. If we work that out, we could go delta T equals Q divided by C times M, where Q is the thermal energy, which is what we found here. C is the specific heat capacity of whatever material you're using. So I just, if you go to matweb.com, you can type in whatever material you're using and they'll give you some numbers. So I just have some numbers here. Let's say we think we're going to work between 150 and 200 degrees. We could just use that number. So anything outside of that range, that number wouldn't quite be accurate, but you'll still get some results. And then M is just mass of the rotor. So I have front left, front right, rear left, rear right. And then we'll get the change of temperature. So we're starting off with ambient. And so until we actually apply the brakes are just going to be an ambient temperature. So here, matweb.com, type in a material. So let's say 1018 steel. Click whichever one you want. And then you'll get specific heat capacity. Some of the materials have more than others. Some of them have none. And some of them will give you quite a few numbers for a larger temperature range. So the more data within the range of temperatures your brakes are going to do, the better. And we can fit a line to these numbers. So what I just copied the numbers here, and then I just took between 100 and 150, I just put 125 right in the middle. And I put all the numbers here, and I made them into joules per kilogram Celsius, since I'm working with kilograms, not grams. And you can plot it, and then in Excel, if you go to the chart stuff, in one of these, layout, you can add a trend line, you can fit a polynomial, or I just did linear. And then if you click display equation on chart, you'll get this equation. So then I just went into Visual Basic. And then I made my own function, specific heat capacity. I just input the temperature, put in that formula I got from the chart, and it's going to spit out a number for me. All right, for cooling, we have this formula. The temperature for a given time is the temperature in environment plus your initial temperature minus environment exponential to the negative RT, where R is HA over CM. So H is the convection coefficient times the area of the brake rotor. So the area, you want to include all of your slots and drilled throughs. So all of the slots and the holes in there, they're adding area to your brake. And again, we have the specific heat capacity and the mass. So I made this formula if the brake position's greater than 0 and the acceleration is less than 0, so we're under braking. So if we're braking, then it's going to give a formula to increase the heat. And if it's not braking, then it's going to go over the formula I just said to cool the brakes. And here you can see the specific heat capacity I have. It just starts at ambient, and then for any point below that, it just takes the temperature of the cell above it, so the previous temperature of the brake rotors. So then in Excel, just copy and paste that all the way down to the bottom of the data that we got from optimum lap. So if we plot the temperature per time, this is what we get. We get the front and the rear. Front left, front right, they're the same temperature, same with rear left, rear right, so they're just overlaid. But there we go, 1 lap. This is a simulation of the heat that we expect to get into our brakes. And if we wanted to, we could take our optimal lap data, copy paste it, and then do multiple laps. So I think I have 7 laps here. We can see how the temperature rises and eventually we reach a plateau for this specific track. So let's say your car's finished and you actually go race. You can compare the real data to your simulation data. So I do have some real data here. It's anything, the blue lines here. I don't know the actual specs of the car. I don't know the convection coefficient. I don't know the mass of the rotors or the size, any of it. So it doesn't really match. It wouldn't match. Well, you can do the simulations to see if your real data and your sim do match or whatever kind of variance there may be. But there's going to be variance because it is a simulation. Simulations are all wrong, but we can have an idea or validate your simulation to your real world data depending on how in depth and complex you make your simulation. So here we just have 1 lap. Again, the blue ones are actual data, the red are from the simulation. We do see they both rise, but not at the same amount because, again, I don't know the actual specs of the car that this data came from. So we have 1 lap on the left, and on the right we have an entire, I think 6 or 7 laps. You can see 5,000 meters compared to 35,000 over here. In these cases, you can, maybe they don't match exactly here, but you may be able to get an idea of, for whatever circuit you're running, the maximum brake temperature, where in this case they kind of match. So they might not match exactly as far as how much they go up, but you may get an idea of the maximum brake temperature you're going to see. And then using that, you can then choose brake pads, because brake pads are going to have different coefficient of friction for different temperatures. So next we can look at that. So if we go to, let's say, Willwood or whatever manufacturer for your brake pads you're going to use, they should have a temperature versus coefficient of friction graph. So we just randomly chose this BP20 compound, and you can see over temperature what the coefficient of friction will be. See, after around 500 degrees Fahrenheit or so, you can see that it drops down. So you probably want to work in this range. Based off your simulation, you can choose your brake pad that you think you're going to need. And as we saw, the front was way hotter than the rear. You may want to choose a different front and rear brake pad depending on the temperatures that they're going to see. So taking that data from Willwood for that BP20 brake pad, I just looked at the chart for the temperatures and roughly what the coefficient of friction is and just put those down. They're not accurate. You could ask the companies for the actual data, but I just went looking at the chart just to get something down. But you may want to actually ask the manufacturer for the exact numbers on that chart. Then I just converted it, the degrees Fahrenheit to the degrees Celsius, and plotted that. And again, I got a trend line. One thing with the trend lines, you may want to go to format. It was general, change it to number, and I just put 20 decimal places because the numbers it was given me before wasn't accurate. So I got my trend line. Again, I made a function for it, and then I just used that function here with the degrees Celsius to see how it fits, and it pretty much overlays the data that I input. So this formula here, this trend line or polynomial, is fitting pretty well to the data I entered. So I went in, I made a function, and I took the calculations to go from pedal force and pedal ratio all the way to rotor torque, and then solved for pedal force. So I enter rotor torque, pedal ratio, mass of cylinder size, number of pistons, the caliper size, coefficient of friction, which I'm going to use the formula here based off of temperature, and then rotor diameter, pedal ratio. And I input that, and then from that it's going to give me a pedal force. And I'll show you what I did with this. So I took that formula and I just did an if the rotor torque is greater than 0, then to use that pedal force function that I created. So I did 4 different ones, front and rear, but I used the coefficient of friction where it's just constant, and then I did another column using that coefficient of friction function that I made that's based off of the temperature. So the coefficient of friction would be based off the temperature of the rotors. So again, I did one with the constant coefficient of friction of just 0.47, which is what we did all the previous calculations before. And then I did one where the coefficient of friction is based off temperature using the chart we got from Willwood. So then I plotted the pedal force versus time, and I have with the constant with the constant coefficient of frictions in blue, and the one with the changing's red, and then dashed line for the rear. So we can zoom in. So if we zoom in here, we can see the constant coefficient of friction's the same, they overlap. But for the temperature dependent, we can see here, for whatever acceleration was going on here, the rear required more pedal force because of it had a lower coefficient of friction than the front. If we go to the end, so at the end we can see that the front's requiring more pedal force than the rear, because at whatever temperatures they're seeing, the front's seeing less coefficient of friction, requiring more brake pressure. So you're not gonna, if you're given this over 350 newtons of force here, the rear is gonna lock up. So your brakes aren't being that efficient as a system because the rear is locking up and the front still has more to give. So this is important to choose the brake pads for whatever temperatures you're gonna see, knowing that the front and rear could have different temperatures. So you can always use this simulation where, because let's say you want to use the same front and rear pad because you're using the same front and rear caliper, so you don't want multiple parts, you just want to have the same interchangeable parts between front and rear, you can start messing around, seeing what the mass does if you change it. So decreasing your mass is getting the rear brakes hotter, or maybe convection coefficient. It's harder to change. It's where you're changing brake ducts and slots and holes in your brakes to change this. And I'll show you later, but finding this value is probably the hardest thing of this whole exercise. And then changing the brake area, so more slots, more holes. So let's say you increase the brake area, causes it to cool more. So maybe you don't want slots and holes in the rear brake. So it's a lot of iteration going between CAD and CFD and this spreadsheet to try to get the front and rear brakes within temperatures that you can use depending on what brake pads you have. But it's going to take some iterations, but using the simulation, you can do it before you're actually manufacturing. So you don't have to manufacture and spend a bunch of money on all these different brake rotors and brake ducts, whatever you're going to be using for your vehicle. So using CFD, you can find the convection coefficient for your brake rotors. It's somewhat advanced, at least for me. I'm not an expert with CFD, so it was a little time consuming to learn this and figure it out. But you can do it using whatever CFD package. It may or may not have combination of flow plus thermal simulations in there. This one I did, and it gave me a heat flux and then temperature for inside and outside face of the rotor, because the open side of the rotor, so you see we have the side of the rotor with the upright, and the other side the rotor is covered by the wheel, so it's not seeing as much flow. So we actually saw different temperatures, different heat flux on each side of the rotor. But I just took the heat flux and the different temperatures and got an average for my simulation just to simplify things. So I got one number, and then as you saw on the spreadsheet, I just used kind of random numbers just for show the difference of front and rear rotors. But you can do this. There's also a paper, I'll, if I remember, put a link in the description, of just using basic shapes, the expected convection coefficient for different shapes, combining them. It's a pretty good paper where if you don't have CFD, you can use that to approximate it, get somewhere close to use in simulations. Another thing I did is I took from the simulation data from the previous spreadsheet the acceleration, the pedal force based off of the changing coefficient of friction based on temperature. So I got pedal force required to the front and the rear, and then the temperature of the front and rear brakes. And I just made this spreadsheet. I filtered out any acceleration greater than 0, so I only took accelerations under braking and also when there's pedal force applied. And then I just saved this as a CSV. So I took that CSV, put it into a Python notebook, and I created a contour plot. So this is the pedal force for the front and per acceleration. So the more acceleration, obviously you need more pedal force, but also put the brake temperature. So we can see here, looking at the chart or the color scale, as temperature increases, we require more brake force because the coefficient of friction at these temperatures starts reducing based off that BP20 brake pad that we're looking at. And did the same for the rear. We see it's the opposite. As temperature increases, you actually require less pedal force. So this fake car that we created in the simulation has pretty bad brakes because the front needs more brake force, pedal force, as the temperature increases, but the rear is opposite. So your brake balance is going to change greatly as the brakes start to heat up. So the balance may be good cold, but as they start to increase the brake temperature, then your brake balance is going to be off, and you're going to start having reduced brake capacity during your event. So if you didn't want to change your brake rotors or anything else, or if you don't have a brake bias adjustment in car, then you may consider, or I would definitely consider for this specific example, different front and rear brake pads. So they have different coefficient of friction based off the temperatures that we're expecting to see. So that's it for this. I hope this helps you with brake design, and I'm not an expert on this, especially with CFD stuff. So if you have any comments, experience, please let me know so we can all learn together.